you have done it, and am totally impressed. So I'm very happy to be with you today and try to share some of my thoughts. I'm going to start with an example of some work that we've been doing and have been working with mostly teachers right now, trying to help them think a little bit about things that are in the news. And so one of the things that we're all familiar with is the pandemic and the impact that it's had on our lives, both professionally and personally. And the other thing is it's brought mathematics into the forefront of the public media, and people are talking and thinking about words and terms that they have never talked about before. And so my colleague, Tom Dick, and I decided that it would be great if we could help students understand what some of these words meant. And so we designed an activity where we started, we didn't focus on the pandemic per se. We started with just suppose you had a class of 20 students and you say that 10% of them are immune for whatever reason. They had the vaccination, or they were already had the disease. And each person transmits the disease to 2 other people. They're contagious for 1 day with this disease. And we have these 2 questions: how long before the epidemic ends? What proportion of the population will contact the disease before the epidemic ends? And so we're going to do this by simulation. And so we have 20 participants. And I actually do this with the teachers and the students. And I change the number of participants depending upon how many we have in the group. And so we have 1 to 20 who stand and they hold little signs, and participants 19 and 20 sit down because they're the 10% immune. I generate a random number from 1 to 18 for a newly infected person. That person enters the room and infects another person. And so here's my class. And the newly infected person turned out to be randomly generated number 15. So they sit down. And number 15, it infects person number 8 and person number 18, just randomly generating 2 more random numbers. And we continue this process until every time I generate a random number, it's already been generated. That person is already sitting down. This introduces students to the concept of herd immunity, where herd immunity is the percent of the starting population of 20 that remains, that is sitting down. These are the people that have contacted the disease. And the ones that are left are the potential people who never did contact the disease. So once we do that simulation physically, we move to technology. This is showing you an example of using Inspire. You can do the same thing on almost any other thing. For sure, it works on the 84. And you generate ordered pairs, where this set of ordered pairs here has nothing to do with the physical proximity of the elements, but each point is representing a person in this now population of 100. And we keep the same conditions, and we fill out a spreadsheet, and we repeat the same process. We generate a random number. This time it was number 16, and that person becomes infected, and they infect 2 other people. And we continue this process until we have to keep track of the data. And I'm going to come back to this several times. I didn't realize how this kept popping up to me. When we do this with teachers, the first thing that they say is, oh, we need to give kids a table so that they can collect the data really efficiently. And my contention is, which I learned actually from the Freudenthal Institute, MIC folks, is that tables can be a hindrance to the way students think about stuff. So rather than giving them this nice table, we just make sure that as they get going, we stop and have them look at how they're collecting their data, recording, because it's really important. If you generate a random number that has already been generated, then that's not a newly infected person, and that reduces the number of newly infected people that you get. So you have to keep really good track. And it's interesting to note how different students approach different ways of record keeping. And you finally end up to a point where you generated, this time we generated these 4 random numbers. They had already been generated. So we had reached what we call the herd immunity threshold. And in this case, it took 9 days. And you can see the little gray dots. Those were the susceptible people that never got infected. And so we had a 70% herd immunity threshold. In other words, 70% of the population had to contact the disease before the disease died out. And we collect the data from the individual students working, or pairs of students. Actually, I usually have them work in 3s. One to kind of run the, keep track on the computer, one to keep track of the numbers, and the other one to generate the random numbers, so that we have kind of the kids working together. So we collect the data because we really, one of the big deals here is that we care about the variability. So often when things happen in the real world, the mathematical model is exact, and people tend to think that that's exactly what should happen. And when it doesn't in a different community, then they get upset because the mathematics is not telling the story. Well, mathematics doesn't tell the story of variability. And that's one of the big important things. So collecting these results and letting kids see that under the same conditions, just by chance, you could have a herd immunity threshold of anywhere from 74% to say 80% or 81%. You can stop there if you're working with 8th graders or 9th graders. But if you are working with students who have a little bit of understanding of statistics, you could actually do things like standard deviations or talk about estimated confidence interval, and you can go different places with that. We then move to a program that allows them to change all of the different kinds of inputs, so that you can have, this one has 1,000 people, and we can use different inputs. We get different outputs for what it looks like. We get tables, we get graphs. And here, this is the susceptible, this is the recovered, and this is the those that were infected. And there's some very nice conversations that you can have, especially with students that are either in Algebra 2 or 3rd year of high school mathematics, as well as some nice calculus things about the relationships between a couple of these graphs, what the points of inflection mean. And people always want to know, what does the point of intersection tell you between those graphs? One of the questions that came up early on when kids were exploring these data is, what does changing the initial percent immune do? So this is kind of like, how many people do we need to have vaccinated in a population? So we ran the simulations with 10% vaccinated, 50% vaccinated, and 85% vaccinated. And as you can see, there's really very different distributions. This one I'm looking at right here is the length of time until the disease dies out. And you can see the big spread. You can see with 10%, there's very little variability. The disease lasts anywhere from 15 to 25 days, about 10 days span there, difference. And you can see here, when you get up to 85%, for the most part, the disease is over. It dies out with like 8 days or less. So very big difference just in the length of the spread. And here's the herd immunity threshold. And this one has some interesting things. When it's 10%, the herd immunity, so that's 10% vaccinated. The herd immunity threshold is all the way up around 80, 90, 95%. So almost everybody gets the disease before the herd immunity threshold or the disease stops, and that we've reached the herd immunity threshold. This one is interesting. This is the 50%. And this is a nice place for kids to think about the chances here. And if this were a workshop, I would stop and actually have you guys all tell me about this. But thinking about it means that actually, if half the people are already vaccinated, the first infected person that comes into the room or into the community has a 50% chance of getting someone who's already been vaccinated. So in some portion of the time, they're going to infect two people, both who have already been vaccinated. And the chances of that happening are enough to make a significant dent here in what the distribution looks like. Now, obviously, when 85% of the people have been vaccinated, your herd immunity threshold is about 85.8%. So very few of the people actually go ahead and contact the disease. So 85% threshold is a pretty good threshold to stop the spread of the disease. This is another way of looking at that data that was suggested to me by a statistician who works with the COVID data in the state of Texas. And this one says what percent are protected. So what percent of the susceptible are protected? So when you only have a 10% vaccinated population, only 2% of the unvaccinated are protected. And only 10% here, but 99% of the unvaccinated are protected if you go to an 85% herd immunity threshold. So, and one of the things that we like to do in working with this is we always kind of try to bring things together. And every time I see something that has logarithms in it, I get excited. So we close this off with having a conversation about other diseases and what kids see in this graph. And I kind of like this because one of my first questions is, after they've thought about what the graph looks like, one of my first questions is, what would this graph look like if it were not in logarithmic scale? So this is the number of people infected by each sick person. Notice that measles, that one infects a lot of people. It's got a really high transmission rate, but it's not very serious. It doesn't have very high fatality rate, whereas bird flu and Ebola have extremely high fatality rate, but they don't infect very many people, probably because it's so deadly. People die before they have a chance to infect too other people. So these activities, we've got a bunch of them, have been designed using a bunch of principles. And one is the informal before formal, where you start with explorations. This is very similar to the kind of things that we did with MIC, where you don't, that's why Kuno is cited there, because it's that notion of grappling with the idea before you make it formal. We delay definitions. We don't start with them. We try to help kids get an understanding of why we needed the definition and what it might work for. We scaffold the steps. We try to move through to allow the concept images to change and so that ideas make sense. We do a lot of reasoning from visual displays. That's kind of the core way of making sense. And then finally, we try to have kids communicate and extend their ideas. So what I wanted to talk about now is the kind of agenda is what is data science, some frameworks, some connections to literacies, a little bit about the research, a couple of other examples and implications for the school curriculum. So you're not supposed to make sense out of this, but it's just to show you that the definition of data science goes all over the place, from very formal to very whatever. And these definitions have been growing since about the year 2000 or maybe earlier. I find that for my own work, the definition that's cleanest and easiest is the one that comes from the International Data Science Schools Project. And it's the science of learning from data. And it's important, I think, for people to understand that it's a blend of computing, of content knowledge, math and statistical knowledge. Sometimes the math is a little bit invisible, maybe less visible than the statistical knowledge, but it's still important there. And something to do with domain expertise. So in the real world, when you do data science, you really have to have a knowledge of the domain from which the data come. And it occurs in a cyclic process. So here is one of the data cycles that I've actually been using, that we've been using in our work. And it comes from North Carolina State, Holly Lynn Lee and her colleagues And it actually has these steps that are pretty simple, obvious steps for the data science process. And I just want to point out how these steps, what they kind of mean, and they are sense making. Notice the idea of considering and gathering data. So it's not closed to just creating your own data through an experiment. It's considering what other data sources. A lot of data science works with secondary sources, not primary sources. And so it's important to remember that these data have been gathered for probably another purpose than what people might be doing with them when they see them in some of the data science places. The next idea is that you have to process the data. This involves a lot of data moves, some words that Paul has used in his work. And one of the big things is manipulating and transforming data because of the units and the scales and the magnitude. And so you start by using some kind of a provided data set that's a little bit clean, and eventually go to more open searches for kids. And the exploring, the visualizing, it's important to realize here that we're not constrained in data science, way not constrained by two things, actually. I should have maybe mentioned this, that data is not just numbers. Data can be pictures, it can be sounds, it can be diagrams, data, it can be body movements, it can be any kind of thing that you can collect and begin to analyze. And the same is true about the visual representations, the visualization. It's not just box plots and dot plots and bar graphs, although that's a lot of what basically kids start with. But it's important to understand the role of multi-variables in this data science world, that color and shape and size, heat maps, these things are all legitimate ways to visualize, and I haven't even begun to list them all. Whoops. The other piece of it here is the modeling part, that one of the things that we have to be really careful of, at least in the United States, sorry about that, is that mathematical modeling is deterministic. And so there's one input for one output. So when you look at it, you really, it's very function based, and you get one input for one output. And a statistical model shows that variability. There's just like growing plants in MIC's growth unit, where for a given day, you might have 5 different plant heights for plants that all started from growing at the same time. So one of the things that I thought I would do was look at how these things compare between statistics and data science. And the first thing that's important is back to this notion of consider the data. The early Gaze document, some of you might be familiar with that, laid out a set of kind of a trajectory, a learning trajectory for coming to understand and do statistical investigations for K-12 students. And it started only with collect data. And in the new Gaze, which was put out in 2020, they added consider the data. So collecting the data meant you were practically always working with primary sources. You were generating the data in some way yourself. Sometimes you would use observational data, but considering the data says, okay, let me just look at these data that I found on the web, or these data that other people collected. So this is a big, big shift in the statistical investigation from ASA. 3 major differences between data science. It's the processing of the data, the considering the models, and the communication. Notice that the Gaze says interpret the results. It's kind of implied that you would communicate them, but the data science and in the real world, really it ends with proposing some kind of an action. There's another data, a science cycle, not a data cycle, a statistical cycle, that comes from the Wild and Vannecook work, the PPDAC cycle. And again, there's a lot of overlap and similarity, but this notion of sampling, design, and hypothesis generation, that's not necessarily a part of data science, where here they don't have considering models and they don't have considering data, okay? And so essentially the really difference is that statistics uses mathematical models to quantify relationships. Data science involves the modeling process, but it starts with huge amounts of data. And it doesn't, the data sets aren't clean. And the notion of designing experiments and looking at regressions and statistical tests is no longer kind of the core or the general focus of what the statistical purpose that's involved in data science is. So I said I would look at the connection between data science and some of the literacies. And I really think that the statement at the bottom, after doing a whole bunch of work here, probably the only thing that people, when they talk about these literacies, agree on is that there's no real agreement about what those terms mean. It is clear that they are not as in depth thinking about what the notion of data, and they clearly do not involve any coding necessarily in what they do. Computational thinking, however, is different. Paul shared the Weintrop's computational thinking taxonomy with us at Michigan State, and there's a big overlap between computational thinking and data sciences. And the overlap is big enough so that Rob Gold, who has done a lot of work in data science, thinks about data science as a synthesis of statistics and computational thinking, where we put these ideas together. Andy Rubin, who's also done a lot of work in both statistics and data science, laid out 5 ideas from statistics that are still really valuable in thinking about work in data science. The context, data science is all about the context. That's why contextual knowledge is part of that diagram about what goes into data science. Again, the notion of variability, the idea of aggregate, not just finding aggregate values, but understanding why they're necessary and how we should be using them are often not addressed. And visualization, we talked about that. That's just still really important. And inference, you do need to think about inference in data science, particularly maybe not the formal inference as much as an informal inference ideas in knowing how you can generalize, if at all, from what you're doing. So the herd immunity problem actually was one of our looks at a way to think about a data science activity. We had to generate the data because there were no available data. We actually visualized using different representations. The scatter plot was an important visualization of how the herd immunity gradually, the number of infected people gradually increases and the number of susceptible people gradually decreases. That's a really important visualization as you go through the process. We didn't here increase the data complexity so much as we changed assumptions. So when we get to the software package, you can click and change all the different assumptions. The need for coding, sometimes you have to transform the data. Here we didn't particularly do that, but you had to code in order to get that program to work. And so the data science herd immunity is one example. Another example comes from the Better Life Index. This is the OECD countries. And this one, the data are all these variables. I think there's 27. I don't know. I think I ran out of the alphabet anyway in Inspire. And they look at the 37 OECD countries and then 4 other countries. And one of the interesting, nice things about this data set is that they explicitly reference the source by clicking on those little question marks, and they give you a sense of what it is. You can go look up the source, so that kids can talk about where the data comes from, what do they mean, how are they collected, so kids can actually pay attention to that how, why, what, when, and where notion. And the data themselves here are not nice. There's little dots for missing values. And so you have to think about how to deal with those missing values. And at a surface level, you can do some simple plots. This is earnings against life expectancy and employment rate. And you can look to see that there doesn't seem to be very much of a pattern between earnings and life expectancy, which I guess one would suspect. You can see here that if I look at pollution and air pollution and the percent that think their water quality is okay, Iceland is way ahead of the rest of the OECD countries. The United States is kind of the middle of the pack. This one gives us just looking at some different percents about what the United States is for some of the different variables that are in there. We're making use of this linked highlighting so that I can see all of the variables that go to the United States. But one of the things that happens is the data are all these different things. They're dollars and percents and averages and years and micrograms per cubic meter. And so you can't really analyze the data without doing something to transform them or think about it in some way. And so one of the things that you can do is use some programs, get some coding in there so that you can manage the data, create graphs, or perform computations. And this can be done two ways. Right now, what we're doing is we're not teaching the kids how to do the code. We're providing the code, the different things that they might want to look at, and letting them make a choice, like shiny apps. So here's one of the ways that you can look at this is you can say, okay, let's just do a proportion of the maximum best value for any category, and then look at how each individual data point, how that rates in comparison to the maximum. And so you can get different kinds of representations. So if you sum up those proportional values, you can look at the impact overall and you see some interesting things. And you're not probably surprised to see that the ones that were rated pretty low several of them were from South America. Notice that Greece and Hungary and Iceland actually also rates pretty low, Ireland. So one of the questions to think about is what's going on here. I will point out that when I noticed Japan rated pretty low here, I was interested in why Japan would rate pretty low. It turns out that there's some data missing on Japan that wasn't accounted for, and that made it very, very low rated. Here's where you can look comparing the Netherlands by using the same proportion. So you can see that the Netherlands is relatively high in the upper quartile in terms of earnings, pretty high in terms of employment rate, and the percent of people that think that they are in good health. Not so good, very good in homicides because you have very few of them. This is the United States. No, this is not the United States. This one's the United States. This one I think is Chile. But you can see, you can make, kids can start to make comparisons using different kinds of visualizations. Another one that they might want to choose, and this would be for students who have a little bit of a background in statistics, although they don't have to have very much. They just have to know that we're trying to standardize these data scores by making use of the mean and the standard deviation. And so here we're looking at the z-scores and interpreting what happens here. So for example, the Netherlands is slightly below average in life expectancy, nothing compared to the United States, however. And notice that this is only a subset. We filtered out all of the OECD countries. Kind of a random choice here. I took a lot of European countries. And here we look at the air pollution, and we can see that Netherlands is a little bit highlighted there, is a little bit above average in terms of their air pollution. The United States is a little bit better. Norway is very good. They have pretty good air. Finland is very good. So gives you an idea of how the data science ideas might fit in there. And here's another way a program was used to create a different kind of a graph. This is a spoke graph, which is not native to the functionality on Inspire, but which can be made to go through and look at all of the variables and compare different countries with reflection on some of the different categories. So we've got this kind of principles where they look at what the numbers tell them, think about things informally, delay the definitions. Then we have these elements of the data science cycle that are important to think about for us to look at. And that kind of like looks at the work that we've been doing. So what does the research tell us? Primarily at this stage, the research is observational. And much of it is at the university level, what's going on. And I'm not sure what happens in the Netherlands, but in the United States, it varies dramatically from university to university. The universities have their own data science department. Michigan State has one. In others, the data science is a part of the statistics department. It could be part of the math department. It could even be a part of another content area. It might be in the College of Natural Sciences. It might be in an economics course. So it depends very much on the university and who kind of the driving people were to get the program started. I thought this was very good. This is a reflection from somebody who was in a university course. And it talks about that we're asking students the wrong questions to help them think about data science. And my questions aren't really very good. And this is a point that I need to take in my own work, is to figure out the right ways, the right questions to ask that will focus on something that is more germane than the probability of arriving to work on time. What time should they leave if they want to arrive at work? And that's going to take in a lot more little considerations and not get you with that same, oh, there's some kind of formula to gather the probability. There's some studies that have been done. So the Data for Kids think that third graders can learn data science, but they really have not done any formal work on that. It's the same thing is true with the UCube people from Stanford. They have done some work on the affordances of tools, which actually reflects back on some of the other work that you guys have done at the Freudenthal Institute about not only the way the tools are constructed and what they show, but also on how teachers choose to use them, which is an important thing. And so there's some literature about that. There is a study done by Rob Gold about the Introduction to Data Science project, which was huge for the Los Angeles School District. This was done back in about 2015. It's still going, this project is. The initial results pointed out that teachers were really not well equipped to handle data science investigations, all the way from formulating the right kinds of questions or helping students formulate the right kinds of questions to actually sticking through the whole data science process to the end, which is an important, that's a component of it, is getting all the way to that final end to communicate what you found and try to make some recommendations or convey some important information. The students did seem to understand data better, and they really liked the coding that they learned in the course. Here's a example of a study that we have just done using another one of our activities about the wage gap. It involved 23 students in the 3rd and 4th year of high school. They were enrolled in either a statistics or a quantitative reasoning course. Some familiarity using Inspires in kind of doing the regular statistical things, but really not analyzing data. They might have drawn some regression lines when they did the unit on bivariate data and understood correlation. The teacher's goal was to think about how a graphical representation could help address questions that they posed. The lesson took 1.5 class periods. And we often have, just to get students started kind of in this informal way, would pick some statement like this about the wage gap, and have the kids talk about what they know about wage gap. Have they ever heard of it? Believe it or not, my university pre-service elementary teachers, many of them didn't even recognize that there was a wage gap. So they were kind of impervious to it, which kind of surprised me. When I did this with high school students, they were clueless. But I thought my university students would be a little bit more aware. So the data all come typically from the Census Bureau, and there's a lot of it. So instead of giving kids the data like this, which is unorganized, we actually organize it and put it in tables and actually put it into a TNS file or into an 84 program that people can use. And this teacher decided that she was going to give the kids the opportunity. They looked at Google Drive. They looked at the data on Google Drive and looked at all the numbers. And her 3 questions that she had driving this lesson was, what do you see? What do you care about? And what are you curious about? And after the class discussions, and she was hoping that that 3rd question, what are you curious about, would help them formulate the question that they were interested in investigating. And she used Navigator, the system where you can share student screens. There's other ways to do that kind of screen sharing since the existence of the Navigator. This teacher happened to have that software. That allowed her to actually walk around the room. There was no formal lectures. It allowed her to walk around the room and to make observations like, I think Michael down here, I don't know if you can see Michael, you probably can't, but Michael has looked at the Hispanic men and the Black men, and not realizing that the year is lost. So any trend he sees is not over time. There's not really much of a trend here anyway, but this idea that he's only looking at the income, not at the year, is not going to be really useful for him. Some kids, just like Stay, just looked at this and thought about the numbers and thought about, well, let me just check about when the differences are going to get to be 0 and project when that will happen. Some kids were very fancy. This was just male and female, the difference between men and women. Some kids looked at the income for 4 different races and tried to make comparisons. Some kids, like Walkman, had a little trouble here because they're struggling with categorical data. They wanted to look at all of the occupations, and then they used a scatter plot, and it's not a really informative graph. You can undo it and make sense out of it, but it's a little difficult to do. But the Navigator allowed both students to see each other's work and to go ask questions about what someone else was doing if they didn't understand. And it also allowed the teacher to move around and intervene where it was necessary. I have this data, we just got this data a couple of weeks ago, so I haven't really been able to look at it very much. But the students were engaged and really into this. Like one of the teacher said, the kids worked from bell to bell. They were really interested and involved. The outcomes, many struggle to communicate. They often, and I find this all the time in my statistics course for elementary teachers, they communicate only in words or only in math, numbers. So the first one I decided to analyze, that's because I'm a white Hispanic male. It amazes me how much higher, but it didn't go beyond that. It just used these words. It didn't even necessarily show a graph. There, the second dot there, men make more than women. They always have, and they probably always will. Actually gets at a really root problem of data science and looking at analyzing data, is that sometimes people ignore, and this is a very common thing to do, people ignore the data in view of their own personal observations. So they kind of like think the data are really not telling the truth. They didn't get all the data. And so that's a problem, an attitudinal and understanding problem. Many students just wrote out some kind of mathematical formulas or use numbers and expect that the viewer, the observer will understand, which in data science is totally not feasible, because one of the roles of the data scientist is to communicate to someone who is not in the field what these numbers and graphs and representations mean. Some of the kids were very, very clear about writing and using their graphs, but they were also a little bit inconsistent in understanding what the graphs meant. So this is an example of someone who followed the teacher's instructions very carefully, but didn't notice that the gap between the women and Black women, all women and Black women, was increasing. And so made two statements about the graphs have never intersected. Well, looks like they've intersected someplace, maybe not within the realm of the data, but at least they should have noticed that. So one of the things that I wanted to say here before I went on to the next one of the things that didn't happen here is that in this activity, we had built in a peer review process, and the teacher ran out of time before she could do that. But the peer review process would have had another student read and critique this student's work. And perhaps the goal is that by that peer review process, the person who was doing the critiquing with a sheet of questions that deliberately focused on, I really don't think I understood this. So it gives the kids particular things to answer. And this might not have gotten through if the teacher had had time to actually implement that process. So implications for the school curriculum. Starting early, I think we have to pay attention to something that in the United States, it's not really happening. It's kind of like people are now just discovering data science or working with data and are not paying attention to the work that was done by the Use Numbers Project and other similar work that was done way back in the late 80s and early 90s. And there was a lot of research that was done right then about how students understand summary measures and what they do with graphing data and how they think about different representations, bar graphs. And I think it's important for us to figure out what students should learn and what they don't have to learn, as well as when it should be learned. That fits into this last one down there. Gaze 2 describes a possible learning trajectory. We don't know where this fits into the curriculum, and that's an important thing to consider and think about how to do that. Gaze is set up on 3 levels for the K-12 system. And it's kind of the intuition is that you say level A goes for elementary, level B for middle school, level C for high school. But their point, the authors of Gaze, firmly believe that no matter where you start, if you just start doing the statistics in high school, then you still need to go through all 3 levels. One of the problems we have in the United States right now is even if students go through the first 2 levels before they get to high high school tends to actually repeat those two levels, like not being convinced that kids come with the right skills, and maybe they don't, but this is a problem. The kids should be free to make representations by hand. Sometimes technology is harder. Not everybody has Tinkerplots. Well, it's actually not even available, not right now, publicly actually. And so it's hard to make some innovative representations. So we need to be on the lookout for how to help kids find ways, maybe more shiny applets or little programs that they can bring in. And again, this emphasizing this communication. I would actually say that this communication business transcends what we do in data science, and it should actually be part of what we do in all of our math problems, is helping kids communicate what they're doing with their mathematics. So some issues to consider: the messy data, the idea of who, when, how, the role of tables. If you have ever really tried to deal with some of this data, it's pretty hard to figure out when you have categorical data, what goes on the row or a column. And when you're working with technology, it's really hard to figure out how to label the rows and columns, because when you display the graphs, sometimes the labels you have chosen, which you might have noticed on some of those from the Inspire, the labels you have chosen are not informative because they all start the same way, and there's not enough space for that particular technology in order to get full labels there. So that's a really big problem. Another problem is there's a tendency when people start writing code is to use code and use all sorts of symbols, and that just like disengages students very rapidly. So there's got to be ways to think about how to do coding without relying totally on a batch of symbols that lots of kids are just going to turn off to. And we do need some more research on areas that are misunderstood by students. This tendency to create bar graphs for everything for their data visualization is something that's tough. So here's a census at school example. You can just go and download it and you can get a biggest sample that you want. It's really nice data because it's not clean and usable. And here was one of the things my elementary pre-service students turned into me. They did the arm spans of 11th graders. And not the person that turned this in, and nobody recognized it, that there was something wrong here. These 4 data points were not, something had gone wrong, and they just blithely ignore it and don't pay any attention to it until you finally kind of have to help them notice that maybe those people measured in inches instead of centimeters or something. So tables, here's another example from Rob Gold about how when tables are in textbooks, they're typically not in the kind of format that's useful. And so thinking about looking at the way we use tables, when you use tables to convey information, are we using them in the appropriate way? This is a pretty bad example. It comes from Gaze 1 about a length of radish seedlings. And there's so many things that are missing. It's almost impossible to interpret the table. And here's a way at least that collects it and gives us identifies the seeds by number. And so I can track them down. I can't remember if we did that in growth, but that's important. So I just thinking about tables made me think about Snakewood. And Snakewood is something that came from Symbols and Patterns from MIC. And in the original book, we had a table for the students to fill out. And when I was working with students with this, I realized that the table was constraining their thinking, and tried it without any tables and let them organize their own way of accumulating and putting the information together. The conversations were much better. I learned more about what they were thinking, and they learned more about what made good organizational how to organize the data so that it was more accessible and would help them better answer the questions that they were looking at. So those are just another example of a table. So here's another piece that's important. There's shifts in concepts that we often ignore these shifts. And this is a space where I haven't read very much about any research, but it's really hard. And maybe it's this mean as balance point versus mean as fair share is the subtle move between moving kids thinking of bar graphs, which is what we've got here with the dogs and their bags of dog food. So basically this is a bar graph, but here, down here, the dog is gone. And instead we're looking at there are two dogs that didn't have any dog food. And so that's a way different way of thinking about this. So here my axis in a sense was was a dog who each could have had a name. Here my axis is the number of bags and the names of the dogs are gone. And that's how we think about the mean as balance point is as we fair share, we get closer to the balance point. But this shift is really complicated. And I think it maybe has something to do with why students are not really convinced about looking at the aggregate and thinking about ways to describe everything. They're very reluctant to lose the name of the dog. Another shift is, so here was some work on understanding margin of error from Soldana and Thompson. And their work, the students didn't do really well. One of the things I think was, this was back in 2014, that it was actually probably done a little bit earlier, and their software put everything into histograms. I think that's a very different way than when kids can actually see the dots that you can do now. So the software has made the kind of understanding what's inside of those bars a much better way and more to think about. So here's some things to think about that are important about preparing teachers and what does the teaching look like. And some of them come from me and some from Rob and some from Andy. And so there's a lot of places to go. Just like data science is not really well defined, we don't have much research yet about what's going on in the places. There are a lot of places in the United States where many people are doing data science, often out of school, not in school. So they have data science clubs, they have after school activities that engage kids in data science. But it's not in any systematic way for the most part. And it's not clear that anybody's doing any research on how those things are actually working. So I'm going to stop sharing and see if anybody has any comments or questions that they want to ask. I'm sorry I rattled on for so long.
Thank you so much, Gail. Very rich, different directions material. So there are some applause. And please go ahead with the questions, comments. Zoom provides this nice opportunity to see everyone who put on camera. So if you have an option to turn on your camera, you're very welcome to do so. Yes, Michiel.
Yeah, well, first of all, thank you very much, Gail, for this really nice and extensive overview of an important topic. And well, you raised a lot of questions, so yeah, we could discuss some of these questions because, well, what are the answers? I was in particular interested in two issues. The one was the context matters, so the what, when, and how of data. So maybe first ask there, because that's also very important nowadays, I think, because we more and more, since data is guiding our lives more and more. We are more aware of possible biases, or that there are often biases. Almost always there is bias in data, I think. So it's really important to know the context, and that is also maybe a reason why some people become a bit skeptical or ignorant of data, because it's so easy to manipulate and to get out of it what serves your reasoning. And yeah, we now have in the Netherlands from yesterday, again, data showing that our basic skills are going down. And then I think, yeah, where does this data come from, and how is it collected, and what does it say? So how to address that in education, this problem of data bias, that you must be aware that there is bias in your data. Is that something you mentioned it a bit, but do you have experience with it?
So I have not ever had too much feedback from students about the data that we've been using, but a lot of my data has been like data from the census or like the OECD, although there's questions about the OECD data that are worth probing. And so I think a lot of it depends on the position that the teacher has about where am I putting my emphasis? Because you can spend a lot of time chasing down, for instance, why were some of those variables missing for Japan? We know that Japan has a high quality education and most of the students graduate from high school. What went wrong in that particular case? Why did that happen? Rob Gold has in his 2016 paper that he did at the IASC roundtable has some examples of where deeper probing into data reveals some insights. I am a little nervous about doing this with 2 young children, although you kind of want them to be sure. So for example, one of the things I do with my elementary students is they talk about the number of pets that they had when they were in 4th grade. And so they give me an answer. And then I start asking questions because it's not clear that they knew what they were answering. Like, how many fish? If I have fish, is it 1 pet? Or if I have 10 fish, is it 10 pets? Can I count my imaginary dog? In 4th grade, I had an imaginary dog. So I try to help them see in ways that little kids could understand that the data answer might not actually be the right answer to the question you thought you were asking. But it's a hard thing to do. It's as well as the ethics and the whole, that we didn't talk at all about the AI, but that's another piece that can get really messy. So, I mean, it's a place we have to think about. It's a good point.
Yeah, thank you.
Thank you. And I think Ad has a question in the chat, which is in a similar direction. Would you like to follow on that also?
Yeah,
I think bias in data is probably not too difficult for 13 to 15-year-old kids. It should start somewhere in there.
rather abstract concept, because I can imagine that you can tell a story with data. You can ask some questions, but bias in data is another level of looking at data.
Yes, and it's not a level that is visible for the most part. It can come in this who, what, how, when. And it is probably most visible when you deal with social issues, such as profiling, stop and search things that we have in the United States. people that have looked hard at those can see that there's that even the way they were collected sometimes leads to bias.
Yeah, thank you. Even so, when students of 13 to 15 years old collect data in their classroom or in their school, you can ask the question, to what extent can we generalize things that we find? And that creates the reflection on the what the data represents, how it's where it's collected, and what might be creating problems in generalizing over a bigger context than the small context often, or the specific context where you collected the data.
Yes.
That also happened with COVID investigations in the beginning, that they missed certain groups in answers. Yeah.
Yeah.
Okay, but
So we shouldn't think of two small kids as not capable of understanding, the other way around. Yes, Paul, and then here you had a hand. But...
Yes, thank you, Anna. Yes, thank you, Gail, for your talk. Very nice to see how you continue to work on things that essentially were already, well, under discussion and debates when we were in the MIC project. I see Monica smiling on that. I have a difficult question, maybe. I'm not sure of it, but it's something that I myself struggle a little bit with, is that we have all these big ideas. We all want to address them, but how are they related? In this case, we have data science, which was in the title of your talk. We also have some people working, or a lot of people working on what they call statistical literacy. So how do these relate? Then you mentioned, okay, now that we have big data sets, we engage in a bit of coding to effectuate these data moves. So coding is another thing. And the fourth element is what is called computational thinking, as you presented in the Weintraub model. So what I'm a bit struggling with, and I'm happy to hear your reaction on the interplay between data science, statistical literacy, coding, computational thinking. They are all in the air. They're not the same, but they also seem to share some common ground. And this is my my struggle. So open to have your reaction if it's not too hard a question.
It's a very hard question.
Sorry.
I would imagine that your colleagues would have a stimulating discussion about where they stand on each of these things and how they interface. I think that would be a really productive conversation to have. We in the United States are now seeing calls for computational thinking to be put into the curriculum, and calls for statistical literacy to be put into the curriculum, and calls for data science to be put into the curriculum. And the curriculum is already overly full because we haven't let go of many things that we probably should let go. So one of the pieces I had in there is assigning procedures to technology. I think we need to revisit how we can do that to maximize opportunities for thinking and learning in other ways, by taking more advantage of the technology to do routines. I'm not sure that will help, but I think it can open space. How we interface all of these literacies is difficult. Another way to do this is what Andy Rubin and Sue Friedel tried to do early on was to make data and thinking with data part of the number world. So you can get a lot of statistical literacy if you can do that. And that kind of left when we got our new Common Core State Standards. They took all the data out of the elementary schools, but they, Sue and Andy had introduced probability using data when kids learned about fractions. So there was kind of an interface and looking at bar graphs and thinking about probabilities. There was an interface of that. There's ways to do that, I think. It's not going to answer your question totally, but there's space.
I didn't count for a final answer, but maybe Anna is going to give the final answer.
No, only to make the situation more complicated, for sure. I was thinking, Gail, also in relation to what you just told, and in a few places in your talk, there was this, we can make technology to draw these nice graphs, or we could make students to organize the information themselves. And you were not even given tables when the data collection was, because as we gain from realistic mathematics, the organizing of the world, that's precisely mathematization. So I'm very much with you in this. And at the same time, you say now, like, we may assign to technology some procedures. So how do you see it? Could the technology be also helpful, not in just outsourcing some procedures, but in the thinking process and organizing data, in coming up with new visualizations?
So when I have watched students, I'm not an expert at this because my technology has been mostly limited to things like Excel and Inspire. I've a little bit with CodeApp and Fathom. And there's pretty much of a limitation as to what the technology can do. Tinkerplots was a great step in opening doors to different ways that kids could conceive of making representations. But that's really not a viable option for everybody right now. But there is a need for technology that does those kinds of things, that allows kids to put together ideas. And I haven't thought about this. But I also really think that a lot of the by hand stuff that we do in just the mathematics should be assigned to the technology. I'm not sure if that answered your question at all.
Thanks. Yeah, that's important. Rahir has a question, and if there are more questions, maybe we have time for 1, 2. Yes.
Yeah, thanks, Gail, for your very nice talk. And when I tried to follow it, and I started thinking about how many of the data that you discuss, like in the beginning, your first experiment, has a statistical model in the background. You have to model it statistically and like probabilistically instead of deterministically, like some really clean physics experiments allow deterministic models. And I believe maybe what's missing in secondary school education is the notion of a probabilistic model versus a deterministic. I wonder, do you sort of agree, and do you see ways to introduce probabilistic models in secondary education?
I would agree totally. So I didn't actually go there, but the herd immunity threshold, that is actually comes out of differential equations. So if you look into it, you'll see that there's a SIR model that is based on differential equations. And you could start there instead of starting with the simulation. But I think this notion of probabilistic modeling is a really important thing, and it can be done as soon as kids start, when they start modeling equations and doing linear expressions and linear graphs. Instead of always using deterministic data, you can use real data that have variability, and then talk a little bit about how that variability might affect the predictive nature of what you're doing, and tie it more closely to the probability models, I think. I don't know if that helps.
Yeah, can I just respond briefly?
Yes.
In the Anna does this. Okay, just I really think, take a notion of random variable. Would you say, oh, let's introduce the idea of random variable for early secondary school, like for 12-year-olds? and relations between random variables. Would that be feasible?
So I'm going to sidestep that and say that a lot of things are feasible. The question that I would ask is it wise? So we have people who teach calculus to 7th graders. They can learn calculus. What they really understand, I'm not sure. I haven't looked at the literature. I don't think the literature proves that. They just show that the kids can pass AP calculus in 6th grade and stuff. Ordinary kids. And the question that I have is, well, is that the appropriate time and place for calculus? And that's what I think. That's why I think these learning trajectories. And that's why I remember, Monica, we struggled over an algebra trajectory. We struggled about how to put the ideas together in ways that made sense. And so that we tried to make it a wise choice about where we had algebra in grade 5 and grade 6 and grade 7 and grade 8. Not because we couldn't have put it together in a different order, but we came up with an order and then we were true to that order. I still have a document called Algebra and Math and Context that I value because it shows the struggles that we were going through trying to identify this order. So when you talk about this random variable, I think it's part of a bigger picture that we have to figure out this kind of learning trajectory about how these ideas fit together to maximize what we want out of all of them.
Thank you. I think we very quickly, although it's almost 5, take Pauline's question. We also started much later, so.
Yeah, we will have to leave. Gail, thanks so much for telling this story about the classroom where there are a few immune and where there are a few will be infecting the others. And you started with this Corona model within one classroom. And I think what you did there was in fact already showing kids that there is a way to model a pandemic with the children playing around, in fact, and infecting each other. And I think this is a wonderful way of starting to show kids what it is to model, and from there on then starting the animations, which then creates the variability in all the different ways of modeling. So did you mean that as a model and for students to understand the modeling, or did you mean that as for the kids to understand variability?
Can I say both? So underpinning all this work is obviously the notion of variability. So when you work with data, there's variability. So that was a key idea that I wanted students to understand. My partner, Tom, is a mathematician, and he would have quit. He would not have made the sampling distribution. He would have quit with his first result of the herd immunity and then playing around, and wouldn't have thought about making a sampling distribution to really address the variability, just because that's not how he thinks. I think our goal between the two of us, our goal was both. We were trying to help people understand the modeling idea, as well as the notion that variability is inherent in this situation.
Thank you. Yeah, thank you. Interesting conversation as an addition to very interesting talk and a lot of questions, of course. But thank you very much for the opportunity to think together with you. And this is the end of our today's seminar, which was a bit in a strange environment, and Rahir will announce the next one.
Or maybe.
And it was a really, I do miss my conversations with you all. It was very rewarding and informative. So thanks for letting me share with you.
Thank you.
Thank you, Gail. And then I will end the session with a short announcement of not one, but even 2 talks. So our next speaker will be in a month's time, on May the 9th, I think. Let me just check quickly. Of course, the 12th.
12th.
May the 12th. It will be André Heck from the University of Amsterdam. And well, you receive an invitation. He'll talk about a European project on inquiry-based mathematics teaching. So I invite you all. And then I also would like to announce our last meeting of the academic year, which will be in June. And it will be either the 2nd or the 3rd Thursday of June. This is under consideration.
Most probably 4th, but that's still
4th even.
23rd is 4th.
Okay, so there you go. It might even be the 4th, but it will be a very special one for 2 reasons. First one is that our speaker will be Paul Drijvers. And a second reason is that it will be face-to-face, and we hope to have with those who are there to have a dinner, to have drinks and a dinner afterwards with those people who are there. We don't have a budget for the dinner, but we invite you to join us for a dinner afterwards.
So for those for whom Utrecht is available reach, we're very much inviting, and for others we still create opportunity to join online, but generally the seminars will go online, sometimes with face-to-face meetings. So thanks once again to Gail, and for also early, I guess, morning with us. Yes, and looking forward to see you again in a month.
Thank you. Bye-bye.
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 And thanks for Zoom opportunity, urgent one.
Take that. And Paul, I think you can stop the recording also.
Yeah, I was looking for the button where it is anyway. I did manage to start recording. There it is.
I can even stop it, I think.
Yeah, I think I did.